Swayam Prabha. Digital India. Educated India.
I welcome you all to the first lecture on the course Thermodynamics and Thermal Engineering. The topic is thermodynamic systems. So, the contents that would be delivered during this lecture hours would be introduction about the thermodynamics, history, classical versus statistical thermodynamics, practical applications, thermodynamic system, what are the types of thermodynamic systems, processes and some solved examples. What do you mean by thermodynamics? So, it is a Greek word, actually it is derived from a Greek word therm. Therm means heat, dynamics means power. So, if we add therm and dynamics, it becomes thermodynamics. So, it is a branch of science which deals with energy. Then the question will arise, what do you mean by energy? It is the ability to cause some change or ability to do work, that is called the energy. Basically, if we see, there are certain laws in the nature like law of conservation of energy. All of us are familiar with this law, which states that energy can neither be created nor be destroyed, but it can be transformed from one form into another form. This thermodynamics has been in existence for a long time. It is not a concept which was developed in the last century or even before that, century before that. It is in existence for a long time. Let us take an example. So, a ball is dropped from a certain height. A ball is dropped from a certain height. So, there are three positions. It is dropped from the position A to C. So, here if you see, initially it has got potential energy of 25 joules. This is just an example only. So, this is just to explain you how the law of conservation of energy is applied. Initially the ball is at rest. So, when an object is at rest, its velocity is 0. So, obviously the kinetic energy will be 0. So, the kinetic energy is 0. So, the total energy in this case, it is the sum of kinetic energy and potential energy. So, that is 25 plus 0 joules, that is 25 joules. As the ball moves from position A to B, the potential energy is converted into kinetic energy. That means the potential energy reduces from 25 joules to less than 25. And the kinetic energy increases from 0. So, in this example I have taken a value of 10 joules potential energy and 15 joules of kinetic energy at the position B. But if we see the total energy, there is no change in the total energy. So, this is what we infer from the law of conservation of energy. One form of energy can be converted into another form, but the total energy of a system remains constant. There will not be any change in the total energy of the system. At the position C, as the ball touches the ground, that means the height is 0, there is no height, h is equal to 0. So, the potential energy is mgh, P equal to m into g into h is equal to 0, that means potential energy is equal to 0. So, the entire potential energy has been converted into kinetic energy, so which is 25 joules of kinetic energy and the potential energy will be 0. So, the total energy remains as 25. So, if you take this example, there are three different locations. In all the three locations, the total energy of the system remains constant, whereas the potential energy and kinetic energy are different at different location. Even if we increase the two more locations like D and E, the total energy at whatever may be the locations which we are introducing, it will remain as 25 joules, as in this case of the example. Maybe the values of potential energy and kinetic energy will be different, obviously it will be different, but the total energy will remain constant. This is one of the laws of our nature. Let us see the brief history, because if we look at the history of thermodynamics, it itself will take even 1 hour to cover it. So, I will cover the history in a very brief time. As I said before, the principles of thermodynamics exist ever since the universe was created, years before, several years before. Though it was it was in existence for a long time. It was not this subject, the principles of thermodynamics, it was not considered as a science until the first steam engine, successful steam engine was invented by Thomas Savery in the year 1697. So, the first successful steam engine was developed in the year 1697 by Thomas Savery. Later, about 15 years from the first successful steam engine, another scientist, Thomas Newcomen, he also successfully developed another steam engine in the year 1712. That was about 15 years from the first invention. These two steam engines, though it was successful, the efficiency of this engine was very less, but it was practically proven. This technology was practically proven. It was not a failure one. Of course, the efficiency of the engine was very less. Subsequently, the first and second laws of thermodynamics came into existence in the year 1850s, and the first time the thermodynamic term was used by Lord Kelvin in the year 1849. Thomson was the other name for Lord Kelvin, and the first book on thermodynamics was published by William Rankine in the year 1859. So, this is about how the principles of thermodynamics, how it became as a science, it has developed into a science. One more thing, as far as the first two successful steam engine inventions were concerned, though these two engines had a very low efficiency, very less efficiency, it was an eye opener for the scientists who followed them to make innovative, a lot of inventions, lot of innovations, lot of developments in the field of thermodynamics. Let us see the difference between classical thermodynamics and statistical thermodynamics. There are two approaches by which the thermodynamics subject can be studied. One is classical, another one is thermodynamics. The classical approach of thermodynamics, it is also called as macroscopic approach, and the statistical thermodynamic approach of thermodynamics is called as microscopic approach. What do you mean by macroscopic approach and what is a microscopic approach? Macro means, as the name indicates, macro is something which is not a minute level, it is at a large level. Micro is something which is at a micro level. So, here in the macroscopic approach of thermodynamics, that is the classical thermodynamics, the analysis is carried out at a macro level, that is at the matter level, whereas in case of microscopic approach or statistical thermodynamics, the analysis is carried out at the molecular level. For example, I will give a practical example like pressure exerted by a gas. The pressure exerted by a gas is due to the momentum change of the molecules, which is due to the collision of these molecules, but we do not see at a micro level. So, we see only at a macro level. So, that is called a classical approach of thermodynamics. The second, another difference is, in the case of classical thermodynamics, the properties such as pressure, temperature, volume are used to describe a system. So, any system if we take, there are certain basic properties. Those properties are pressure, temperature, specific volume, density, all these are properties of a system. Whereas in case of statistical thermodynamics, the properties such as velocity, kinetic energy and momentum are used to describe a system. So, that is what I told in case of that example. The pressure exerted by a gas on a system. So, that is due to the molecular momentum and due to the collision of the molecule. In case of classical thermodynamics, the analysis is, it provides solutions to thermodynamic problems in a simpler way, whereas statistical thermodynamics, it is somewhat a detailed and a comprehensive analysis, and sometimes the finding solutions to the thermodynamic problems becomes a lengthier one, becomes a time consuming one. So, this is the schematic representation of a classical and statistical thermodynamics. If you take the picture which is on the left side, that is the classical one, where the focus is on the entire system. You do not find any type of molecules. It is not analyzed at a micro level, So, that is the focus is entirely on the system. This is like container or something like that which contains some fluid, it could be a liquid or a gas. So, when I focus on the entire system at the macro level, it is referred to as classical thermodynamics or a macroscopic approach. The diagram which is showing on the right side, if you see, there are some red color dots which indicates molecules, which represents the molecules of the present in the system. So, here if we see, the moment we see the schematic, our focus is paid at the molecular level. We are focusing our attention on the molecular level. Suppose as all of us know, any object or a substance, it is made up of molecules. The behavior of such an object or this one, it is directly depending upon the properties of these molecules. Let us see now some practical applications of this subject, thermodynamics. If we discuss about the practical applications, the list will be a very big one. So, in order to cover the other topics of the thermodynamic systems, so I have just mentioned very few applications right from the historical period. So, the first one is the steam engine, which was developed by Hero of Alexandria, Egypt. So, this is a diagram which I have taken from the Wikipedia open source. So, here if you see this portion is the you can see some vapors, some form of vapor, which is nothing but the steam. So, here the heat is provided from the bottom, okay, like something like a wood is burnt. This was way back in several years before. So, the wood is burnt. The heat liberated is used to convert the water which is in this spherical container, and the water is converted into steam, and there are two nozzles which are there, which of course the function of the nozzle is to enhance the velocity, because the steam normally which is generated even in the boiler or whatever the steam generating device, it has high pressure and temperature, but the velocity may not be that much significant. So, generally the nozzles are used to enhance the velocity. So, this was one practical application which was invented by Hero of Alexandria, Egypt. So, this was considered as one of the steam engine in those period. The second one is the invention by Denis Papin. Denis Papin, he was the scientist who invented pressure cooker. So, after successfully developing the pressure cooker, he has invented the first piston cylinder arrangement type steam engine, that is a reciprocating type steam engine. So, the first piston cylinder steam engine was developed by him. So, that is one of the practical applications of thermodynamics. Steam engine developed by James Watt, that is shown in this slide. So, that is an improved version of the steam engines that were developed by the previous scientists before him. Summarize the practical applications of the thermodynamics. As I said, the list is a very big one. If you think of any activity, there will not be any, hardly it's difficult to see activity without the application of thermodynamics. Aircraft, rocket engine, jet engine, propulsion system, automobile engine, compressor, power plants, air conditioning, refrigeration system, solar collectors, water heater which are used in our homes for residential applications, spacecraft. These are only a few of the applications which I have mentioned. The best example for thermodynamics is human body. The food which we take, that is the energy input to our body. All of us know that our body loses heat to the ambient. We do work. The blood circulates, the blood is circulated by the heart to various parts of this one, and lots of the body cells, numerous number of body cells, it performs various tasks. So, if you see the human body, the food which is stored in the form of chemical energy, it is converted into useful work. It is also converted into heat which is rejected to the ambient, in the form of sweat through the skin of our body, and the remaining one is stored as the internal energy. As the topic of the lecture 1 indicates, the system, thermodynamic system, now we are going to see what is a thermodynamic system, what are all the types of system, how it is applied to in real time problems. What do you mean by a system? System is nothing but a region or a space on which the attention is focused. Suppose if I have a piston cylinder which contains gas or any fluid for that matter. Suppose if you want to see what is happening, let us say the piston is moving up from the bottom dead center to the top dead center. Top dead center and bottom dead center in the piston cylinder arrangement are the terminologies which are very common. Top dead center is the center which is at the topmost position of the cylinder, where beyond which the piston cannot move. Similarly, the BDC refers to the bottom dead center of this one in the cylinder, where below which the piston cannot move. So, the distance between the TDC and the BDC, it is referred to as stroke, that is the volume swept by the piston between TDC and BDC, it is called stroke volume or swept volume. So, in the case of, in the example which I told, the piston cylinder arrangement contains some fluid. So, suppose if the piston is moving from bottom dead center to top dead center, it is a compression process. It is an example for a compression process. So, here I can consider the fluid which is present, because my focus is only on the fluid, whether it is a compression process or an expansion process. If I am focusing on the fluid which is present inside the piston cylinder arrangement, it is considered as a system. Surrounding, anything which is external to the system, which is outside the system, it is called as surrounding. And there is a region which separates the system from the surrounding. There is a region between the system and the surrounding which is called a boundary, So, this is what a system. Here I have just taken a like a box. This box could be a piston cylinder arrangement, it can be a turbine, it could be a compressor, it could be a engine, it could be anything depending upon the applications. I have just indicated as a box, so that whatever we place it like this, where we focus our attention, we pay our attention. So, that is called a system, and this is the surrounding, or this is region, any region outside this system, it is called surrounding. And boundary separates the system from the surrounding. Of course, boundary, it is not a visible one, it is an imaginary one which separates the system from the surrounding. Types of thermodynamic system. So, open system, the other name for open system is control volume. Closed system, which is also called as control mass, and isolated system. Now, let us see what do you mean by the open system. Before seeing the definition of the open system, if you take any engineering devices, most of the engineering devices are of open system. Most of the engineering devices that we use in the day to day, this one. So, as mentioned, it is also called as control volume. In case of open system, both mass transfer as well as energy transfer takes place. What do you mean by mass transfer and energy transfer? For example, we have a system in which mass is coming in and going out. Similarly, energy is coming into the system and it is going out. So, there is movement of mass across the system and movement of transfer of energy. So, if both mass and energy transfer are there in a system, such a system is referred to as open system. Example is turbine. I have just given only one example. There are, as I mentioned before, most of the engineering devices are of open system type. Closed system. In case of closed system, the mass is fixed one. There is no mass transfer, only energy transfer takes place. A simple example is a fluid contained in a piston cylinder arrangement. Assuming that the fluid is taken through the suction valve and both the suction and the discharge valve are closed. Let us take 1 kg of fluid in a piston cylinder. I am just compressing it continuously, compressing the fluid continuously with the help of the piston. As long as the discharge valve is open or the delivery valve is open, there is no movement of mass of that fluid moving out of the system. So, here there is no mass transfer, there is only transfer of energy. Work is done on the fluid by the piston. Isolated system. Isolated system is a system in which there is no mass transfer as well as energy transfer. A typical example is a thermoflask, where once we store a liquid at a particular temperature, until we open the flask, until we open the thermoflask, whatever the mass which is contained inside the thermoflask will continue to be there. And if it is well insulated, if it is well properly fabricated, there is no heat loss. That means the temperature also is going to remain the same. Of course, it will not remain same for throughout for n number of days. There is no interaction. Between the system and the surrounding. There is no interaction between the system and the surrounding. Neither energy transfer nor mass transfer takes place. So, these are all the types of systems which are there. I have taken a practical example of a water heater which is used for residential applications, water heater. So, how this example can be considered as a open system, closed system and isolated system. So, the same example under different operating conditions, it can be considered as an open system, closed system or an isolated system. So, this is the water heater. The cold water which is entering into the heater is shown in with the help of a blue color arrow, and the green color arrow is the one which represents the hot water outlet. So, this is a geyser, it is a heat geyser, it is not a solar based system. Of course, for a solar based water heater also this whatever the conditions which I have given here, it is applicable. So, let us assume first the heater is switched on. I am opening the cold water inlet valve is open. So, water is from the overhead tank, it is filling the water heater, and the hot water outlet is valve is also simultaneously open. So, heater is on, cold water inlet valve is open, hot water inlet valve is also open. So, here there is mass is crossing, mass transfer is there, energy transfer is also there, because the water is being heated using the electrical energy which is a high grade energy. So, under this condition, when the heater is on, cold water valve and the hot water outlet valve are open, this example is considered as a open system, both mass transfer as well as energy transfer. Now, when the second condition, the heater is on, the cold water valve inlet valve and the hot water outlet valve both are closed, that means whatever the water which is contained inside the heater, it will be heated continuously until I switch off the heater, There is no further water supplied to the heater through the inlet valve from the overhead tank, and I am not taking the hot water also simultaneously. So, both the valves are closed. There is only energy transfer, there is no mass transfer. So, whatever the water which is stored in the heater, it will be heated until the heater is switched off. So, it becomes a closed system in this case. Now, when we switch off the heater and also at the same time both the valves are closed. So, there is no mass transfer, there is no into the system, or there is no mass transfer from the system, there is no energy transfer, there is no interaction between the system and the surrounding. So, this case becomes an isolated system. So, the same example can be considered as an open system, closed system and isolated system according to the various operating conditions. This can be is similar to the solar water heater also. Of course, the mode of heating only is different. In this case of geyser, we use high grade electrical energy to heat the water, whereas in case of solar water heater system, we use a renewable source of energy to heat the water. Let us see some of the various thermodynamic process. There are 4 to 5 basic processes which are involved. We will see one by one. Process, the first one is isochoric, so which is shown on the left side of the slide. So, what do you mean by isochoric process? It is a constant volume process. You can see the process, I have considered a process 1 to 2. 1 is the initial state and 2 is the final state. Volume at 1 is equal to volume at 2. So, here the line is perpendicular to x axis is the volume and y axis is the pressure. Arrow mark is pointed in the upward direction. So, it is like the pressure is increasing. In this case, the pressure is increasing. Suppose if the arrow is pointed towards in the downward direction, it becomes initial P1 will be at the top and 2 will be at the bottom. So, the pressure is decreasing in that case, but still the volume remains constant. So, V1 is equal to V2. A simple example for this isochoric process is container containing a liquid, say let us take water. So, when we heat water in a container, say from 30 degree to this one, Or let us take pressure cooker, water, you use heat the water with the help of this one in a pressure cooker container. So, if you take 1 liter water and place it inside and heat it, the temperature will increase, the pressure will increase, but the volume of the system will remain the same. There is no change, volume of the water is not going to change, either increase or decrease, as long as this sensible heating is provided. Next, isobaric process. Isobaric process is a constant pressure process. The other name for isobaric process is constant pressure. The other name for isochoric process is constant volume process. In case of isochoric process, it is perpendicular to x axis. In this case, in isobaric, it will be perpendicular to y axis, that is parallel to x axis. So, here I have mentioned the arrow mark in the positive x axis. So, that means V2 is greater than V1, but pressure at 1 is equal to pressure at 2. Pressure at 1 is equal to pressure at 2. So, this is also plotted on a PV diagram, constant pressure process, constant pressure process. An example for this process is like when we inflate the bicycle tire with the air, compressed air in the two-wheeler workshop or a cycle shop. So, what happens is, as the air is used to inflate the tire, so you can see the gauge showing almost the same value of pressure, though the volume of the system in this case is the tire, which as it gets inflated it changes. So, there is a very common example for this type of process. Adiabatic process. What do you mean by adiabatic? The term adiabatic means there is no heat transfer. Q is equal to 0. Q is equal to 0. So, on a PV diagram, an adiabatic process can be inclined by a curve like this. So, again here also the arrow marks can be pointed towards upward or towards downward. If it is pointed towards upward, it becomes compression, adiabatic compression, and if it is pointed towards downward, it becomes adiabatic expansion process. Shape of the curve will be similar for both compression and expansion. Only the difference can be inferred only in the direction in which the arrow is marked. So, in this adiabatic process, so for example, if you take P1 is greater than P2 and volume at 1 is less than volume at, pressure increases and volume. So, actually this is a process 2 to 1, actually it should be 1 to 2, it is I have mentioned as 2 to 1. So, this is process 2 to 1, normally it should be 1 to 2. So, since I have used 2 as the initial state, 1 is the final state in this case. And the basic equation for an adiabatic process is PV power gamma is equal to constant. What is this gamma? This gamma is equal to Cp by Cv, that is index of compression or expansion. If it is a compression process, it is called as index of compression. For air, Cp is 1.005 kilojoule per kg Kelvin and Cv is 0.717 kilojoule per kg Kelvin. So, it is the ratio of specific heat at constant pressure to specific heat at constant volume, specific heat at constant pressure to specific heat at constant volume. So, this is equal to 1.4 for air. The units gets cancelled. So, gamma is equal to 1.4 for air. So, the ratio of specific heat to specific heat, one at constant pressure and another at constant volume, is called gamma. So, PV power 1.4 is for adiabatic process. So, here the pressure P1 is greater than P2 and volume V2 is greater than V1, or in other words P1 is greater than P2 and V1 less than V2. An example for this adiabatic process, suppose if you take a insulated chamber which contains a fluid. So, it does not permit outside heat to enter into the system or inside heat to go out of the system. Suppose if I consider a insulated chamber, as I told, that is the system, that my focus is on the insulated chamber. I am focusing my attention on the insulated, so that becomes the system. So, it is well insulated, assuming that there is no loss. So, neither heat flows from outside into the system or heat flows from the inside portion of the insulated chamber to the outside one. Like a thermoflask also can be considered as an example for an adiabatics process. The fourth type of process which we are going to see is isothermal process. Isothermal, temperature remains constant. Thermal means term, that is heat related, measuring the temperature. So, it is a constant temperature process. It is a constant temperature process. The coordinates, that is x axis and y axis, I have plotted on a temperature entropy diagram, because to make the students understand easily. So, this is plotted on a TS diagram. Temperature is on the y axis, entropy is represented by the letter S, that is on the x axis. So, a constant temperature process T1 is equal to T2, and here again in this case S2 is greater than S1, that is entropy at the final state, 2 is greater than entropy as the initial state. Example for a constant temperature process, we can say during condensation of steam in the thermal power plant or steam power plant, or condensation of refrigerant in case of a refrigeration system or an air conditioning system in the condenser. So, what happens during that process is there is a phase change from vapor to liquid. There is a phase change from vapor to liquid. So, during that process, the heat is released by that working fluid, which is removed by the coolant circulated to the condenser. That coolant can be either air or water. Normally, in case of small capacity systems, the condensers are air cooled. In case of large systems, the condenser is water cooled. So, what is happening during that phase change, when the vapor is converted into liquid, the temperature remains constant. So, you can take condensation process, evaporation process. During evaporation is just opposite to condensation, where the liquid is converted into vapor, during that process, that is a latent, it is also an example for a latent heat. So, during that process, the temperature of the system remains constant. So, that is a isothermal process. The fifth process which we are going to see is isentropic process. The other name for isentropic process is reversible adiabatic process. So, where the entropy is constant, Here T2 is greater than T1, and because the entropy is constant, it is S1 is equal to S2. If you see the applications of this project, this is a process which is used for ideal conditions. Achieving a perfect isentropic process, in reality it is a challenging one. So, it is mostly this process is used whenever we analyze an ideal thermodynamic cycle. So, to summarize the different types of process: isochoric process, the other name for isochoric process is constant volume process, isobaric process or constant pressure process, adiabatic process, a process in which there is no heat transfer, Q is equal to 0. For this process alone, I have taken the initial state as 2 and the final state as 1. You can take the other way also, initial state can be 2, 1 and the final state can be 2. Fourth process is the isothermal process, which is a constant temperature process, and isentropic process is the fifth one, which is also called as reversible adiabatic process. Let us see some solved examples based on the concepts and the theory which we have seen about the thermodynamic systems and the various processes. First numerical question is: a certain amount of an ideal gas is initially at a pressure P1 and a temperature T1. First, it undergoes a constant pressure process such that T2 is equal to 0.75 T1. Then it undergoes a constant volume process such that T3 is equal to 0.5 times T1. Find the ratio of final volume to initial volume of the ideal gas. So, let us solve this problem. I have given the solution in the PPT. Let us solve one by one. Step by step, I am going to solve this problem. So, first let us draw the diagram, PV diagram. Pressure in the y axis and volume in the x axis. Gas is initially at a pressure P1 and T1. First, it undergoes a constant pressure process 1 to 2. So, this is 1 initial state, final state is 2, constant pressure process. So, if you extend this line, P1 is equal to P2. P1 is equal to P2. If you see the problem, the temperature at state point 2 is equal to 0.75 times T1. Temperature at 2 is equal to 0.75 times T1. It is given that the gas undergoes a constant volume process after that. Okay. So, next it undergoes a constant. So, this is state 2 and next it undergoes from 2 to 3 constant volume process. So, here if you extend this line, volume at 2 is equal to volume at 3, volume at 2 equal to volume at 3. And if you see the problem, it is given the temperature at 3 is equal to 0.5 times T1. T1. So, let us write the given data. T2 in terms of T1 it is given 0.75 times and T3 in terms of T1 is also given. So, from the process 1 to 2 we can write P1 is equal to P2 and from process 2 to 3 we can write V2 is equal to V3. So, find the ratio of the final volume to the initial volume of the ideal gas. Final volume to the initial volume. So, this will be volume number, volume 1. And this will be pressure 3. So, we have to find out final volume to initial volume. So, initial volume is V1 final volume is equal to V3 from 1 to 2 the first process, then from 2 to 3. So, this is the final volume. So, we have to find out find V3 by V1, V3 by V1. So, let us first consider the process 1 to 2. Consider the process 1 to 2. 1 to 2 is a constant volume process. So, applying the Charles law to this process, consider the process 1 to 2, it is V equal to constant, V equal to constant, or we can take this ideal equation of state PV equal to, if we take mass as 1, PV equal to MRT. So, PV equal to RT. Apply this equation to state 1. So, if we write state 1, P1 V1 is equal to R into T1, R is a constant, gas constant, and at state 2 we can write P2 V2 is equal to R into T2. Let us take this as equation number 1 and this is equation number 2. Divide equation 1 by 2, we will get P1 V1 by P2 V2 is equal to R into T1 by R into T2. Sorry, 1 to 2 is constant pressure process, not constant volume. So, here P1 is equal to P2. So, this will become V1 by V2. So, these two terms will get cancelled, P1 and P2 will get cancelled, V1 by V2 R term will get cancelled equal to T1 by T2, or V2 by V1 is equal to T2 by T1. V2 by V1 is equal to T2 by T1. So, that is what I have written here, V2 by V1 equal to T2 by T1, and from this you can write T2 by T1 is equal to 0.75. 0.75 is nothing but 3 by 4. So, similarly here also we can convert it into fraction. T3 by T1 can be written as T3 by T1 is equal to 0.5. 0.5 is nothing but half. So, which can be written as 1 by 2. So, now from the given data T2 by T1 is equal to 3 by 4, that I am going to substitute here. Three by 4. So, therefore, V2 by V1 is equal to 3 by 4. So, this is about the first process 1 to 2. Now, let us consider the process 2 to 3. 2 to 3 is constant volume process, or directly we can calculate the ratio of final volume to initial volume. Final volume is V3, initial volume is V2. If you look at the PV diagram, V2 is equal to V3, V2 is equal to V3. Therefore, without using the second given data, this T3 by T1 equal to 1 by 2, we can find out V3 is nothing but V2 by V1, since V3 is equal to V2. So, what is V2 by V1? V2 by V1 is equal to 3 by 4. Therefore, the ratio of final volume to initial volume is equal to 3 by 4. So, that is what we have been asked to find out, find the ratio of the final volume to the initial volume of the ideal gas. So, let us move to the second numerical question. This is the question example number 2, solved example number 2. A football was inflated to a gauge pressure of 1 bar when the ambient temperature was 15 degrees centigrade. When the game started next day, the air temperature at the stadium was 5 degrees centigrade. Assuming that the volume of the football remains constant at 2500 centimeter cube, determine the gauge pressure of air in the football. So, first let us write given data. This is numerical question number 2. Let us write the given data one by one. A football was inflated to a gauge pressure of 1 bar. So, P1 is equal to gauge pressure 1 equal to let us take gauge pressure as Pg1 equal to 1 bar, 100 kilopascal, 100 kilopascal. Temperature 1 is given as 15 degrees centigrade. So, T1 is equal to 15 degrees centigrade. So, that is TA ambient temperature is T1, which is equal, convert this temperature from centigrade into Kelvin, add 273. So, 15 plus 273, 288 Kelvin. This is T1. The temperature of the air at the stadium is 5 degree centigrade. So, that is T2. T2 is equal to 5 degree centigrade. So, that is equal to, add 273, it becomes 278 Kelvin. Volume of the football is given 2500 centimeter cube. It is constant. Hundred centimeter is 1 meter. So, therefore, 1 centimeter is 1 by 100 centimeter, that is 10 power minus 2. So, here we have got centimeter cube. So, 10 power minus 2 the whole cube, which becomes 10 power minus 6. So, this is equal to 2500 into centimeter to meter is 10 power minus 2. This is centimeter cube. So, 10 power minus 2 the whole cube, that is equal to 2500 into 10 power minus 6 meter cube. So, we have to determine the gauge pressure of the air in the football. So, let us solve this problem. There are two methods by which we can solve this problem. Let us see the first method, method 1. The gauge pressure is given. There is a formula to convert to find out the total pressure of the system. Suppose if this is the system, you have a pressure gauge is fixed. This is the pressure gauge. This pressure gauge will give only the gauge pressure of the system, not the absolute pressure, not the absolute pressure. If you want to convert the gauge pressure into absolute pressure, atmospheric pressure has to be added. So, this is a very basic one. Absolute pressure is equal to gauge pressure plus atmospheric pressure So, this is equal to So, let us take this as P1. P1 is the absolute pressure. When we write given data in the form of a pressure like P1, T1, P1 is absolute pressure, it is not gauge pressure. If it is gauge pressure, we will use the letter G, Pg1. So, P1 is equal to P gauge, this is, let me write the formula again, P1 is equal to Pg1 plus P suffix ATM. So, this is equal to 100, atmospheric pressure is 101.325 kilopascal. So, it is 201 point, correct, 201.325 kilopascal. This is the absolute pressure at point number 1. And it is clearly given assuming that the volume of the football remains constant. So, it is a constant volume process. Process 1 to 2 is constant volume, that is V equal to constant. So, similarly for this process also we can apply the equation of state of an ideal gas, that is PV equal to RT. So, you will get P1 V1 is equal to RT1 at state 1 P2 V2 equal to R into T2 at state 2. Volume is constant. So, you divide this equation, this is equation 1, this is equation 2. Divide equation 1 by 2, we will get P1 V1 by P2 V2 is equal to R into T1 by R into T2. The R term will get cancelled. Volume term also will get cancelled because V1 is equal to V2 because the process is a constant pressure, a constant volume 1. So, V1 is equal to V2. So, therefore, P1 by P2 is equal to T1 by T2. Or in other words, P2 by P1 is equal to T2 by T1. Now, these values are given, temperature 1, temperature 2 is given, temperature 1 is 288 Kelvin, temperature at point 2 is state 2 is 5 degrees centigrade, that is 278 Kelvin. So, let us substitute the values. So, P2 divided by P1 is 201 kilopascal, 201.325. T2 is 278, sorry, T2 is 278 and T1 is 288. So, when you calculate, you will get P2 as 93 kilopascal, 93 kilopascal, or divide by 100 to convert the kilopascal into bar, 0.93 bar. This is again absolute pressure at state point 2. This is the absolute pressure at state point 2. Now, in the question we have been asked to find out gauge pressure. So, again using the same formula which we used to convert the gauge pressure into absolute pressure, now the absolute pressure to be converted into gauge pressure. So, we can write P2 is equal to absolute pressure at point number 2 is equal to Pg2 plus P atmospheric. So, this is therefore, Pg2 is equal to sorry, there is one small error in the this one. P2 is 194, P2 is 194, sorry, P2 is 194, 194.32 kilopascal, 194.32 kilopascal. So, that is equal to, let us keep it in kilopascal itself. Now, substitute the value of P2 from this, Pg2 equal to P2 minus P atmospheric pressure. So, this is equal to P2 is 194.32 minus P atmospheric pressure is 101.325. So, 194 minus 101 is 93 kilopascal, that is the gauge pressure at point number 2, gauge pressure at point number 2. So, if you convert into bar, divide by 100, it is 0.93 bar. So, this is the first method to solve this problem. There is a second method, alternate method, which is provided by using the equation of state PV equal to MRT, PV equal to MRT. So, apply this equation for state 1, P1 V1 equal to MRT1. Method 2. So, P1 V1 equal to MRT1. So, let us quickly solve the problem by the second method. P1 V1 equal M R T1, substitute the values and find out the value of M, because P1 is given, V is given, T is given, R is 287 joule per kg Kelvin for air. So, if you find out M value 6.089 into 10 power minus 3 kg, 6.089 into 10 power minus 3 kg. Now, apply the same equation for state 2, P2 V2 equal to MRT2, P2 V2 equal to MRT2, and find out P2 value. P2 value you will get it as 194.32 kilopascal, and from P2 we can find out Pg2, so that is equal to 93 kilopascal. So, there is one more last problem in this lecture. 1 kg of air initially at a temperature of 127 degrees centigrade expands reversibly at a constant pressure until the volume is doubled. Find the magnitude of work transfer. So, it is a constant volume process from constant pressure process. So, the line is perpendicular to y axis. 1 is the initial state, 2 is the final state. Mass is given as 1 kg, temperature, initial temperature is 127, converted into Kelvin, add 273. Final volume is twice the initial volume, pressure is constant. So, the work done for a constant pressure process is cyclic integral 1 to 2 P dV, that is the work. When you integrate, P is constant, so you can take outside the integral. dV, when you integrate dV, it is V, apply the upper limit and lower limit, V2 minus V1, V2 is nothing but 2 V1. So, 2 V1 minus V1 is V1, P1 into V1, both are P1 and V1 can be written using equation of state as MRT1. M is 1, R is 2.287 if it is kilojoule per kg Kelvin, and T1 is 400. So, substituting you will get the work done during this process is approximately 115 kilojoules. So, to summarize, in this lecture we have seen what is the concept of thermodynamics, how it has evolved, brief history of thermodynamics, what do you mean by a system, what is the surrounding, what is the difference, how the system is separated from the surrounding, that is by using boundary. It is an imaginary one, it is not a visible one. Then we have discussed about the types of systems, open system, closed system, isolated system. Then we have solved the numericals. Before solving the numericals, we have seen the various types of processes: isochoric process, constant volume process, that is constant pressure is isobaric, isothermal or constant temperature, adiabatic process, and the last process which we saw is reversible adiabatic process or isentropic process. Then we have solved 3 numerical questions based on these, based on some of the processes which I have covered in this lecture. So, this is about the first lecture on the subject thermodynamics and thermal engineering. Next will be the lecture number 2. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.